Log on, tune in, find out. Another good idea from Cambridge.
And he's going to talk about Higgs bundles for the non-compact dual of the unitary group.
Okay, thank you very much for the opportunity to give this talk here. Is this right? Okay. Okay, so I'm going to talk about some joint work with Oscar Garcia Parada on Higgs bundles. So let's start with a X. Let X be a compact Riemann surface. Of genus G, at least 2. Take G to be a real or complex reductive group. Reductively group. And so let's choose a maximal compact. H is a maximal compact subgroup. And at the Lie algebra level, so we have the Catin evolution at the Lie algebra level of G. And this gives rise to the Catin decomposition. So, Catin decomposition of G, which is like this. So the Lie algebra of G splits as a direct sum of the Lie algebra of H, and this is the complement. So here theta on H is 1, theta on M is -1, and these are orthogonal with respect to the non-degenerate bilinear form which exists on G. Okay, now we can the composition, one of the properties is that if we bracket H with M goes to M, and now we can complexify the Catin decomposition, and from this we obtain the isotropy representation. So H, the complexification of the maximal compact, acts on this vector space MC just by restricting. This is this is the so-called isotropy representation, which is just induced by the adjoint representation of GC on its Lie algebra. So with this, now we can define what is a G-Higgs bundle in this generality. Okay, so a G-Higgs bundle on X is a pair if E, where so E is a holomorphic HC principal bundle on X, and this phi, which is called the Higgs field is a global holomorphic section of the vector bundle with fibers MC coming from the isotropy representation and from this principal bundle. Okay? And then we twisted this with the canonical line bundle. So this is the canonical line bundle. Okay? This is, in this generality, a GX bundle. So let's see some examples. Well, the first one, the easiest one, is when G is compact. When G is compact, so there is no H is G, so there is no M, so the Higgs field must be 0. So when G is compact, a GX bundle is a GC principal bundle. Okay. When G is GLN C, and Higgs bundles, when they were introduced by Hitchin and Simpson, they were introduced, the ones which were introduced were in fact GLNC Higgs bundles. So when G is GLNC, in terms of vector bundles, a GLNC Higgs bundle is a pair so I'm going to write this in terms of vector bundles. It's a pair V phi, where V is a rank n vector bundle, holomorphic vector bundle, and phi is a global endomorphism of V twisted by the canonical line bundle. Okay? For example, if one considers SLNC, then it's the same, but we impose that V as to have trivial determinant, and phi must have trace 0. Okay? So our third example, and this is the one which we are going to work more, is G equals U star 2n. So let me define this in terms of matrices. This is here are the matrices in GL 2nC, such that this condition holds, where Jn is the usual. Okay, this is the U star 2n group. So why are we considering this group? Because what we are going to study here is the number of connected components of the moduli space of GX bundles for this group. This group is a real form of GLN, or GL2n in this case, and for all the other real forms, GLNR, the compact form UN, and UPQ, that problem has already been studied and solved. The problem of the number of connected components of the moduli space for these groups has already been studied and solved by Garcia Prada, Bradlow, and Peter Gotten, and this was the remaining one. So that's the reason. Okay. Now, so let's see what's a Higgs bundle for this group. Yeah.
You don't need to transpose the matrix.
No, I don't think so. No. So the maximal compact here is the compact symplectic group. And so our HC is the symplectic group. And so the Cartan decomposition at the Lie algebra level is then GL2NC plus MC. Okay, and this MC is, so are the matrices. M, this is our MC, and so from this we can see that then a U star 2n Higgs bundle, again in terms of vector bundles, is a triple W omega phi, where so W omega is a symplectic vector bundle just coming from this group, is a symplectic vector bundle, and phi is an endomorphism of W twisted by K, which is symmetric with respect to the symplectic form. Metric with respect to omega. So we write this as 2W. So this means the endomorphisms of W symmetric with respect to omega. Okay. So by the way, this in the title of the talk we say the non-compact dual of the unitary group. This means this group, and the name comes from because this in the Cartan classification of symmetric spaces. This symmetric space is a non-compact dual of this symmetric space. Okay, this is just a note. So we are going to. So the problem is to study the moduli space of these objects, in particular its connected components. Okay. Now, one first thing is to note that obviously the symplectic form gives an isomorphism W to W dual, so the degree of W must be 0. And this is of course related to the fact that this group is simply connected. Okay, that group is simply connected. Okay. Now, let's, in general, there is a stability notion for any G Higgs bundle, stability, semi-stability, and polystability, very general notion, which was obtained in the paper of Garcia Prada, Goten, Peter Goten, and Ignacio Mundet, Ichin Kobayashi. I don't remember the rest of them. In this paper, it's defined a very general notion of semi-stability of these objects. And then there are studied very many examples there. And for each example, the stability is studied and then given a simplified notion of stability for those examples. We have done this also for this group here, and I'm going to state here the simplified stability and semi-stability definitions for these groups. So, which then is the one which is expected to be. So first, we are going to need also the stability for this. So a GLN C Higgs bundle is V-phi, is semi-stable, if the slope of any subbundle of V is smaller or equal if semi-stability than the slope of V for any V prime inside V, which is phi invariant. And phi invariant means that it's preserved by phi. Okay? So the slope is the degree over n in this case. And a U star to n Higgs bundle W omega phi is semi-stable if again if now the slope of this is 0 because the degree is 0. If the degree of any subbundle is less than 0 or equal for any W prime subbundle of W, which is phi invariant and also isotropic. So this is what one was expecting to be. So here we consider all phi invariant subbundles, and here all phi invariant subbundles, but also isotropic. Okay, with respect to the symplectic form. Okay. There is also in that paper, in this paper, it's also analyzed and studied the notion of polystability. I'm not going to write it here, but it can also be simplified for these groups as well. So in general, these stability notions allow the construction in this generality of the moduli space space of Higgs bundles. This was constructed by Alexander Smith in this generality. And what we want is, let's write M for mu a star. And what we want to know is what are the number of connected components of M. Okay. So now let's consider a U star Higgs bundle, and then for each of these objects we consider the following complex of sheaves which goes from here to here. I recall that these were the endomorphisms of W symmetric with respect to the symplectic form, and these ones are the skew symmetric with respect to omega. We have this complex of sheaves which is in general a particular case. In general, for Higgs bundles, here we can take the HC bundle coming, the adjoint bundle of E coming from the adjoint representation, and here we take the bundle coming with fibers MC twisted by K and coming from the isotropy representation. So this complex governs the deformation theory of the object, of the Higgs bundle. In particular, if this one is polystable, so if it represents a smooth point in M, in the moduli space, then the tangent space to M is the first hyper cohomology group of this complex. Now, let me just introduce a new definition. So a G Higgs bundle if E is simple if it has the least number of possible automorphisms. So if the automorphism, the group of automorphisms of Phi is just the center of HC, and then we intersect this with the kernel of the isotropy representation, so that it's an automorphism is compatible with the Higgs field. Okay. So in general, stability of Higgs bundles does not imply that they are simple, contrary to what happens to vector bundles. So, for example, but for G equals GLNC, then in this case stable implies simple. This was proved by Itching, which in this case simple means that the automorphism of V phi is C star, but for U star to n, stable does not imply simple. And this, in this case, simple means that the automorphisms must be, the group of automorphisms must be Z2. So why are we doing this? Because we are to study the number of connected components. In a few moments we are going to introduce some function. We are going to analyze that function, and the study of that function must be done separately on smooth points and in non-smooth points. So that's why we are introducing these notions. Okay. Now we're using a kind of reduced version of this complex. It was proved the following result, proposition. It's in a paper of Bradlow, Garcia Prada, and Gotten, in an upcoming paper. So if E phi is a stable and simple Higgs bundle, and if so from a Higgs bundle if G is a real form of GC, from a Higgs bundle one can construct a GC Higgs bundle. So if E phi is a Higgs bundle, and if the corresponding GC Higgs bundle is stable, then E phi corresponds to a smooth point in N. Okay. So stable, simplicity, and if the GC Higgs bundle is stable, then it's a smooth point in the moduli space. So what we did, now we already know that stable U star Higgs bundles may not be simple. So what we did, we characterized all the ones which are U star Higgs bundles which are stable and non-simple. Let me state that. So first it's from a U star to N Higgs bundle, we can obtain a GL2NC Higgs bundle by obviously simply forgetting the symplectic form. Okay? And this is precisely this case. From a Higgs bundle, one obtains a GC Higgs bundle. So, and now what we proved was the following. So, this is W omega phi is semi-stable if and only if W phi is semi-stable. This viewed as a U star and this viewed as a GLN. W omega phi is stable and simple if and only if this GLN is stable. This then is stable and non-simple. So stable and non-simple are simply the ones which split as direct sum of stable and simple U star. So this is a non-trivial direct sum, R, and each one of these are stable and simple, stable and simple U star Higgs bundle for the corresponding rank. And finally, the polystable ones. I didn't write the definition of polystable, but it's polystable. But we proved this if and only if it is a direct sum. So a U star to n Higgs bundle is polystable if and only if we can write it as a direct sum of GI Higgs bundles, where GI is one of the following groups, where GI is either a U star to Ni or some GLN IC or SP to Ni or UNI. So this Ni. Okay. So a polystable U star Higgs bundle splits as a direct sum of GI Higgs bundles, where each one is one of these Higgs bundles for one of these groups. Okay.
And these stable.
Sorry.
And the summands are stable.
Yes, and the summand. Yes. Like sum of stable. Yes. Right. Okay. Okay. Now, as a corollary, obviously, from this and from 2 says that stable and simple is equivalent that this one is stable. Here, the smoothness criterion was that it had to be stable and simple and stable as a GC. But stable and simple for this case implies that it's stable as a GC. So a stable and simple U star to n Higgs bundle corresponds to a smooth point of the moduli space. Okay. Now let's go to attack our problem, the number of connected components of this space. And so the way to do this is a procedure which was introduced by Hitchin. And in fact, all the other groups that I mentioned, GLNR and UPQ, many others, this was the procedure that was taken to compute the number of connected components. So what one does is to consider the so-called Hitchin functional proper. Hitchin proves that this is proper. Hitchin proper function, which is just by taking the square of the norm of phi. In fact, here I'm cheating a little bit here, because to be rigorous, this is not defined in M, it's defined in the moduli space of the so-called Hitchin equations. But that is homeomorphic to this space through the Hitchin-Kobayashi correspondence, and so we are identifying this a bit. And so this is a proper function, and since it's proper, we know the following. The basic result: if you take M prime in M closed subspace, and if N inside M prime is the subvariety of local minima of F, and let be okay. So if N is connected, then so is M prime. Since F is proper, it attains a minimum on each closed subspace, and if the subvariety of local minima is connected, then it so is M prime. And this is what we are going to do. We are going to analyze the local minimum of this function, and see what happens. So F is in fact up to a multiple. It's a moment map for the S1 action on the moduli space there's an action, S1 action, it's Hamiltonian, and F is a moment map. And so the critical point of F on smooth points. So I'm now restricting to smooth on the smooth locus. Okay. So the critical points of F are the fixed points of this action, and these. So if it is fixed by the S1 action, then, as it was proved by Simpson, we have a decomposition of W, the vector bundle W, as a direct sum of vector bundles, and also a decomposition of the Higgs field, phi equals the sum phi j, where each phi j goes fj to fj plus 1 tensor k. Okay. With respect to this. And then, moreover, we have this symplectic form, and one can see, doing some computations, that this fj is orthogonal to fi unless I is minus j. And this tells us that these indices must be symmetric, so they must be start on minus m and finish on m for this case. So here also. Okay, and now this gives rise to an induced decomposition of the bundle of endomorphisms of W as follows. So we take this as a direct sum of some UKs minus 2m, where each UK is the sum of the homomorphism from fj to fi when I minus j equals k. So this decomposition of W gives rise to this decomposition of the endomorphism of W, UKs, where UK is this. And now what define the following. Consider the skew symmetric endomorphisms of W with respect to omega, and put here k, and this is just the intersection of the skew symmetric endomorphisms of W with UK. I call it with this in this k, and the same thing for the symmetric ones. Okay. Okay. And from this, oh no, okay, yeah. Okay, thank you. And from this, recall that we have this complex. From this, we are going to obtain a subcomplex of that one. So we obtain a subcomplex of weight k of C of that one, just by defining this way. And now the Higgs field, the adjoint, at phi as weight 1, and so this goes to S2WK plus 1. So this is a subcomplex of that one. And so recall that we are always, in this case, on the smooth locus. And now we have this theorem of Bradlow, Garcia Prada, and Gotten, which says that if let W omega phi be a stable and simple U star Higgs bundle. So if it's stable and simple, we have already seen that it's smooth. Then it is a local minimum of f of the Hitching functional if and only if either phi is 0, obviously, or this map, let's call this at phi k. This at phi k is an isomorphism for every k at least 1. So they proved this in general for any group, following some computations made before by Nigel Hitching. And so we have here a criterion which tells us a way that to see if a critical point is a local minimum of the Hitching function or not. And so that's what we did. And we proved that let W omega phi stable and simple. And so our computations, so we went to see when this is an isomorphism for k at least 1. And what we saw is it's never an isomorphism. So the only minimum for this group are the ones which stable and simple minimum are the ones which have phi equals 0. So local minimum. And only if phi is 0. So these are the stable and simple, which is in the smooth locus. So it's in this place that we can use this. But now, if it is stable and possibly non-simple, the Hitching function is additive with respect to direct sums. And we have seen that stable and non-simple are the ones which are direct sum of stable and simple. And so we reduce our problem to lower rank moduli space. And from this we know that in that lower rank, the only minimum are the ones which have phi equals 0. So stable are local minimum if and only if phi equals 0. And the ones which are remaining, the polystable ones. Now the polystable ones also split as a direct sum of stable in lower rank moduli spaces, and possibly for other groups. These groups are compact, so here the Higgs field is automatically 0. And here it's known by the Hitching that the minimum must have phi equals 0. And here as well. So local minimum phi equals 0. So the minimum subvariety here, which is this n here, so n is isomorphic, so phi must be 0, so we only keep the vector bundle. So it's isomorphic to the moduli space of sp2n Higgs bundles, which is the moduli space of symplectic vector bundles. And this is connected. This is isomorphic. Which is connected by Ramanathan proved this. So we now apply this proposition. This is connected, and so now our theorem is that nu star 2n is connected. Okay. Now notice that I said, for example, that one of the other real forms which has already been studied of GLNC was GLNR, and in fact many of the things which happen here are similar to that case. A GLNR Higgs bundle is a vector bundle, now a quadratic form, and phi symmetric. It's very similar. But in this case, the moduli space is not connected. In this space, the moduli space has, I think, 3 times 2 to the 2g connected components. So although all the theory is very similar, the number of connected components here is much bigger. One reason is that here the topological invariant was fixed, was the degree, couldn't vary, but here we have the first and second Stiefel-Whitney classes, so these give rise to much more components. And also, this is the split real form of GLNC, and Itchin proved that for split real forms there is also a special component which also appears, the so-called Itchin component. So although the objects are very similar, the result is quite different. Now, all these studies have been done mainly case by case, group by group. What we are trying to do now is to prove in general, so very important in the fact that this is connected, is the fact that the group is simply connected. So what we are trying to work now, and what we conjecture, is if G is simply connected, then the moduli space Ng is connected. Okay. So what we are trying to do is to take out all these steps, but now for general G, using this. Just one last thing is that for non-abelian Hodge theory gives rise to a homeomorphism from the moduli space of G Higgs bundles and the G character variety, which is this is for general G, but in our case, U star. The space of reductive representations, this means reductive representations of pi 1x in U star divided by the overall conjugation. And so what one proves from what one concludes from that result is that the U star character variety is connected. In general, for any G, one might have to replace this pi 1x by a universal central extension. If G is semi-simple, when we can leave pi1 hex here. If the group is reductive, as this case, this group is reductive, but even though we can prove that since the degree is always 0, this corresponds to representations of pi1x and not from the universal central extension. So from that result, we prove that this is connected. Okay, and that's it. Thank you.
Any question?
Are there known examples where that proposition 2 fails? So stable and simple does not imply that the complex version is stable?
Stable and simple. Well, I don't know. I don't know if any.
But for example, in the real form UPQ, you can have that situation, which is morally sort of related to a non-vanishing of the H2 abstraction. But it is there are situations where PQ, in fact, P equal to Q.
Is there some hope of getting information on like H1 and H2 or something like that?
Of the moduli space. Well, in some cases, if this is smooth, then this is a perfect Morse plot function. So in those cases, one can get some much more information, topological information, like Betty numbers, and so on. But that's only when this is smooth. In general, this is singular. Can have singularities, and then in this case, I don't know. At least for using this function, doesn't seem much. I don't know if there is much hope.
What's the dimension of this space?
For general G, or I think it's 4n squared G minus 1, I think, plus 1, something like this. I'm not sure, but I don't know if there is this one or not. Maybe it's.
But it's the same, I mean, it's the general fact.
Yeah.
In general, meaning for a generic component, the dimension for a real group is half the dimension of the moduli space of the complex.
Mm-hmm.
Not always. There are exotic components that have lower dimension. In this particular case, this is the same dimension of the moduli space of vector bundles. Half the dimension of the moduli space of Higgs bundles, vector Higgs bundles.
Mm-hmm.
Any other questions?